Okay, well, today is we're going to start one of my favorite topics here. We're going to start actually doing a theory of programs. Now, again, as was the case last time, hardly any of this material is in the book, so it might behoove you to take notes. Okay, so now the first thing we need to learn is the concept of what is called the weakest precondition. Okay, so here we go. Weakest precondition. Now, you all know, what are the three parts of a Hoare triple?
Precondition, statement, postcondition.
Precondition, statement, and postcondition is right. And so this precondition is that first part of the Hoare triple. So we know what a precondition is, but now what do we mean by the weakest precondition? This is a really important concept. So here's what we mean by the weakest precondition. Suppose we have this Hoare triple. Q and then X. Now let's just do it. Let's do this example with an assignment statement. We'll illustrate the weakest precondition with an assignment statement. So Q, X gets E. Now this is capital E, which means that's some what? Expression. Okay, so it could be some, arithmetic expression or something. X could be an integer. And then the postcondition R. Okay? So suppose that we have this Hoare triple. Now what's the interpretation of the Hoare triple? If Q is true,
then the statement
executes and terminates,
and the postcondition is guaranteed.
And the postcondition is guaranteed to be true, right? So suppose that this is in fact a valid Hoare triple. In other words, suppose that we do have a precondition here, and we have this here, and we have we have this statement, and we have this postcondition, and suppose that's valid. All right? But now, suppose we have another Hoare triple. Check out this Hoare triple. Here's P for the precondition. X gets expression E, and postcondition R. Now, what's the difference between this Hoare triple and this Hoare triple?
Nothing.
Well, yeah, there's something. The precondition is different. Are you with me? It's got the same statement, it's got the same postcondition, but the preconditions are different, right? Now, furthermore, suppose that not only is this first one valid, suppose this second one is valid also, which is certainly possible. Are you with me? I mean, you can envision that is in fact the case. So suppose these are suppose this and this are two valid Hoare triples with the same program statements, all right, and the same postconditions, as we noted, and the same postconditions, all right? And so there they are, same statements, same postconditions, different preconditions. Now, this Q, right here, and the first one, this Q is called the weakest precondition if the following is true. Okay, so Q is called, so now here's what we mean by the weakest precondition. Q is called the weakest precondition. So weakest precondition if, now check this out. Now, if you have X implies Y, which one is weaker, the X or the Y? You remember how we had what was the weakening, strengthening? Remember those? If you have X implies Y, which one was the weaker? Did we strengthen the precondition and weaken the post? I mean, did we strengthen the antecedent?
I think, yeah, we strengthened the antecedent.
So, if P implies Q, so this is called the weakest precondition if this one implies this one. Are you with me? If this one implies this one, then this one is weaker. So Q is called the weakest precondition if P implies Q for all P that make the Hoare triple valid. For all P that make the Hoare triple valid. In other words, if you can imagine an infinite number of valid Hoare triples, and every single one of those preconditions that would make that Hoare triple, if those imply Q, then Q is the weakest one of all. Are you with me? See? So here, let's do an example. I think if you see an example with numbers, this will help. So here's example. And I think you'll see here now what we mean by weaker and stronger. Okay, so I'm going to write down two Hoare triples here. First Hoare triple is x equals 4 for the precondition. X gets x plus 1 for the statement. And x is less than 7. Now let's think about this. Let's think about this Hoare triple and see if it's valid. Now what's the interpretation? If this is true, and you execute this statement, it will terminate, and this is guaranteed to be true. So I ask you, suppose we know that x equals 4, and we do, x gets x plus 1. Is it guaranteed that x is less than 7? Yeah, so this is valid, right? I mean, we agree that that's valid. Now let me write down another one. Suppose we have this. X is less than 6. X gets x plus 1. Postcondition, x is less than 7. Now, we'll ask the same question. Your observation is correct. If we know that x is less than 6 at the beginning, and we do x gets x plus 1, is it guaranteed that x is less than 7? Yeah. Okay, so this is also valid. Right? Now, do you see, I could write down a whole bunch of other valid ones and have different things here. And you can sort of imagine a lot of the ones that you could, a lot of preconditions that you could put here, right? Okay, but now, note this. But now, what implies what? Does x equal 4 imply x is less than 6? Or does x is less than 6 imply x equals 4? Which, you see what I'm saying? In other words,
I think x equals 4 implies.
yeah. So note that x equals 4 implies x is less than 6, right?
So would any other.
Equal value below 6.
Anything else you can come that would be true is.
Yeah. What's your, okay? So say that again. So
Anything else that would make it valid still would also imply it's less than 6.
Making that the weakest precondition.
Yeah. Now, so can you envision? I mean, can you visualize? I mean, yeah. When you think about it, no other thing that you can put here, or any precondition that you put here that would make this valid is going to do what? Imply x is less than 6.
So that's considered the weakest, but it's also the most succinct and
Valid.
encompassing.
Well, yeah, it is the weakest precondition. Yeah, it's the one that.
The least specific, I guess.
Yes. Yeah, that's a good way of putting it. It's the least specific. It's the one that gives you the most room. Yeah, a quote. Yeah, that's really good. This is really good intuition. This is really good intuition. It's the one that gives you the most room. Yeah. All these informal ways of saying it is so. But the point is, so let's write down any precondition. Any precondition that makes this, now here's what I'm going to do. Watch this. That makes this SR valid. Okay, so we're going to do this in general. That makes this SR. So this is the statement postcondition, valid. Okay, so any precondition that makes this valid implies what? implies x is less than 6. Okay? So what we're saying is that x equals 4 implies x is less than 6. What we're saying is that this one is strong. Okay? So this one is strong.
Can you get any stronger than equals?
Well, yeah, you could. You could go, x, well.
It only gives you one possibility.
Yeah, it does. I mean, we could have examples with less than. I mean, could we have some less thans, or could we have greater thans, or what? And this one is weak. Okay, and what we mean by weak, let me try to write down what you sort of said informally. In other words, it is true. This one is weak. It is true for more values of x. True for more values of x. Actually, it is possible to get even stronger than this. Can you think of it? Could you think of something that's weaker, but that still is not the weakest? Could you think of something that's weaker than this, but still is not as weak?
X is less than or equal to 5, or x is greater than.
X is between 4 and 6.
So greater what?
Not equal 3.
Oh, I don't know. Would that imply x is less than 6?
No.
No, I don't think so. So that wouldn't be valid. But there is something that's even stronger than this. This one is true for more values. This one is only true for one value. How about?
True for no value.
Ah!
True for nothing?
So what would that be?
That's strong. X is greater than 6?
No. Think about it. We're actually going to see it here in a minute. And it might even be up there. Oh, I don't think it's up there. Oh, maybe. Oh. Ooh, well. Anyway. Okay, think about that. That's a good thing for you to think about. Okay, now just one more thing now about notation. So everybody now, what we've done so far is we are giving you the concept of weakest precondition. We haven't done anything formal yet. We haven't done an axiom, right? But this is the meaning. This is the meaning of what we're about to do. Now, one more thing before we get to our actual theorems and axioms. The notation for the weakest precondition. So here's notation. And then after that, we'll get to some good formal proofs. Okay, so notation for the weakest precondition. Here's what it is. WP, so the way we write it is this, lowercase WP, and obviously WP stands for weakest precondition. So you do WP dot S, now this is a 2-dot thing, dot S dot post. Okay? It's kind of a strange notation, but this is the standard in the literature. So WP dot S dot post equivales P. All right? It means that, so this post is post condition. So this means that P, S, the Hoare triple, P, S post. It means that this is valid. Actually, we're just rewriting this. But this notation means that P, S post. So notice the way you do this. The S is here, and the post is here, and the precondition, and that equivales P, the precondition here. So this S dot post is like S is here and post is here. I mean, you see the order. What I mean. So it's kind of like over here when we said this S R. So now on our formal notation, we're going to say S dot R, right? So means that this is valid, and for every Q satisfying what? Now you could probably write the rest. And for every Q satisfying,
S post.
satisfying what? yeah, this is a Hoare triple is valid. And for every Q satisfying, you know, for every other
Other precondition.
every other precondition. So for
Satisfying as post, right?
yeah, well, for every other satisfying
Oh, QS.
QS post, you see what I mean?
Yeah.
Yeah, but anyway, what is true? Q must be what? Yeah, stronger or weaker? Q must be stronger or weaker?
Stronger.
Yes. Q must be stronger than P. And that is, so how do we say that formally? That's the meaning. And now, let's write that example using this notation, and then we get to go to some proofs. So now how do we write, how do we write this example with x plus 1, 7, 4, less than 6, blah, blah, blah. How do we write that now using this notation?
Right.
We write WP. Okay, so here's our example. That's good. So you said we write WP, then what? Dot. Yeah, and since this is kind of a long thing with a gets, we're going to put it in parens. Okay, so this is x gets x plus 1, paren, and then what? Dot.
X less than 7.
Yeah, and here x, we'll put a paren here. X is less than 7. And then that equivales, what does that equivalve? Which is x is less than 6. So this is an example of that. Now does everybody, yeah? Yeah. Now here's what's kind of interesting about this, you guys. Look, what is the type of x is less than 6? It's Boolean. It's either true or false. What's the type of x is less than 7? Boolean. It's either true or false. What's the type of x gets x plus 1? Yeah, this is weird. Because it doesn't have, you know, it actually doesn't have a type. Are you with me? Because what is it? Its type is, well, maybe I guess what we should say is its type is program. You see what I mean? Maybe we should just call it, I never thought about this before, but maybe we should say this is type program. Maybe that's the way we should refer to it. So, because it's not integer, because it's x gets something, yeah, and it's an action that happens in a program. I mean, it's a program statement. So maybe we should say this is type program statement. Okay, you see what I mean? And that's always what's going to happen. When you do WP dot this will be a program statement. And then dot, and this will be a Boolean equivalent. But this whole thing, this WP dot S dot, this Boolean expression, this whole thing is what is this the type of this? Ooh, this will make a good exam question. What's the type of this? WP dot S dot post.
Program.
No.
No, Boolean.
Boolean. It equivals P.
Is it the weakest precondition? Yeah.
Yeah, the type of this, ooh, that would make a good. Yeah, is everybody clear?
Yeah.
The type of this whole thing is Boolean. What's the type of this, of the S? Program statement. And what's the type of post? Boolean. And what's the type of this? Boolean.
So if we're writing the weakest precondition for a 100-line program, we have to put the whole statement in?
Yeah. But what you could do is you could say that whole, here's the way we typically do it whenever we're doing calculations like this. If you like have that list of things, you call that whole, you make up a letter for that whole thing, and you just put that letter in, so you don't have to repeat copying it down all the time. We do that a lot when we do these calculations. We have a long, complicated program statement. You just call it S. And you put S. And also, we actually do this. We do the same thing for these preconditions and postconditions. So we have a long precondition, long postcondition. We normally just make a letter out of it, and we just put the letter there, so you don't have to keep writing the same thing over and over again. Okay? So that's a technique that we will use. Okay, now, all of this, all right, all of this is background so that we will know what the weakest precondition is. Now, but formally, here we have it, a theory of programs. So check this out, you guys. Here we have a theory of programs. And let's take a look now at, and as usual, we start with axioms and then we do theorems, right? And all of the formal methods that we learned all apply. And we can go all the way back. We're going to have to go all the way back to 3-point something to do some of this, right? So you have your equation sheets? Okay, we'll get them out. Do you have your equation sheets? Yes. Which implies, get them out. Anyway. Okay. Example of implies. All right. So let's take a look at our theory of programs. Now, first of all, the very first axiom, P.1, is called excluded miracle. Now, I didn't make this up. This is the way it is in the literature. Okay, this is really called the excluded miracle. And what it is it says WP.S.false equivales false. Now this gets back.
So the precondition of a Hoare triple where the postcondition is false is false.
Yeah.
The weakest precondition.
And now, do you know the answer to this question that we had over here? Do you know the question that we answered? I said this is one.
Yeah, the weakest is false.
Yeah. Oh no, not the weakest.
Strongest.
The strong. Yeah. Okay.
But that is only in the case that the postcondition is false too, right?
Well, I mean, as it turns out.
Can the precondition be false with any? If the precondition is false, nothing happens.
Well, no. Something happens. It's just that well, I mean, S can be any statement. So something can happen.
So the interpretation is, if false is true, then...
Well, yeah. So, yeah. Well, but see, when you say if, well, I know, but yes, that is the interpretation. If false, then what? But anytime you say if false,
then it doesn't matter what the
interpretation is. The whole thing is
true. Right?
Yeah. So that's kind of one way of thinking of it. It's kind of loose, but anyway. Okay. But anyway, so our excluded miracle, it says WP.S.false equivales false. So that's our first axiom. The second, so there are two axioms that define weakest precondition. The second axiom is conjunctivity. So what it says is that if you have a weakest precondition .S.paren x and y. Now, do you remember what that says? I mean, this would be S, and here for the post, you would have x and y, right?
Okay.
And what does that say? It's the weakest precondition .S .x and the weakest precondition .S.
In the postcondition, you can split up into two Hoare triples. If the postcondition doesn't end.
Yes, both of those Hoare triples will be valid.
Right.
If you have a Hoare triple with an and here, then if you wrote that Hoare triple twice, once with the x and once with the y, both of those would be that Hoare triple would be yeah. Anyway. Okay. All right. Now comes and obviously our first theorem we're going to prove, right? We kind of have to do that, yeah. So we can see how these program theorems are proved. Okay, so here we go. P.3, we'll do proof of monotonicity. So here, P.3, proof of monotonicity. All right. Oh, by the way, what does this look like? Do you remember monotonicity? You have your equation sheets? What was the monotonicity that we knew?
Monotonicity of or.
Yeah, let's look at this slide.
P implies Q implies
4.2 and 4.3. It said,
implies.
well, it says, if you know,
If P implies Q, then something with P replaced with something replaced by P implies it replaced by Q.
Q, right. So it's 4.3. This is similar to 4.3. So here, C 4.3, okay? Because 4.3, here what 4.3 says is that if you know that P implies Q, then you know that P and R implies Q and R. So if P implies Q, then the conjuncts, then
We're using
P and...
P.2 to prove this.
Well, I mean, this is a similar, I mean, this is a theorem of monotonicity of and this is...
So I'm saying, aren't we using P.2 to prove this, the axiom?
Oh, I don't. Oh, good question. I don't think so. But maybe here. Well, let me see. Are we going to use 4.3? No, we're not.
No, I said P.2.
Oh, of course. We are going. Oh, yes.
Yeah, that's what
Yeah, we have to. Yeah. In fact, there's no false in here, right? So the only thing we can use is for P.2, right? Okay. So now, do you think we should start with the right-hand side or the left-hand side? Because we're going to do a...
I like the right-hand side.
Actually, I do too. Because the right-hand side has that WP stuff in it. And then we can go back to the WP stuff, right?
Yeah.
So here, so let's start with we'll start with WP dot S dot X implies WP dot S dot Y. Now, what are we going to have to do you think? In order to use P.2,
Something
what do we...
about the definition of implication.
Yes, we're going to have to go back to one of those definitions of implication.
I say we
Good
do,
call. Good call. Very good call. Yes.
Yeah,
Why did you know that? How did you know that?
And, we need the and.
Because you need the and. So which one is that? 3 point...
60.
So we use 3.60, which is what? P implies Q equivales what?
P and Q equivals P.
P and Q equivales P. Man, you guys are good. Okay. And so therefore what do we have? Okay, so tell me what to write down now. This implies this equivales what?
W dot S dot X and WP dot S dot Y.
WP dot S dot X and WP dot S dot Y.
Implies WP.
No.
Or equals
Equivales
WP dot S dot X.
WP dot S dot X. Now, does everybody see how that worked? All right. And now we use P dot 2. So equals, oh, you guys are cool. P dot 2. Okay. And now using P dot 2, WP dot S dot X and WP dot S dot Y is what?
WP dot
S dot,
X and Y.
yeah. WP dot S dot parentheses X and Y, right? Equivales. So we still have this WP dot S dot X.
Now we do
Now this one is tricky. I don't know if...
strengthening 3.76b. No.
Mm,
We have to pull her out of that.
yeah, well, all right. I'm going to have to give this one to you, I think. First of all, do we want
And we want it to
equal? Do we want to imply or follow from?
follow from.
We want it to follow from. So this is going to follow from something. Here's what we're going to have to use. I think it would be hard for you to come up with this. We're going to use Leibniz.
Also looking at.
Oh, good. It's going to be 3 point, so you have your equation sheet?
I would say, wouldn't it be
Which one? 3?
3 is Axiom Leibniz.
Yeah. Can we use that? What does that say?
Something equals something, then E with that replaced by
Yeah, what is E? What is the E here?
W dot S dot.
E, what is E? What E with Z? What is E here? It's 3.83. Maybe we should look at 3.83. Here, let's look at 3.83.
E WP
So-
dot S dot Z.
Yes, very good. So let's look at the axiom Leibniz. E equals F implies E with Z replaced by E equals E with Z replaced by F. So E is an expression, right? And Z is some variable, right? So here, so it's, here, we'll do textual substitution. And what it is E, so we have, what do we have? We have E in here, in 3.83 we have a big E and a little e and a little f, right? We have a big E and a little, so we have, here we have E, big E, a little f. And so what are we saying that is? What's the expression?
WP.S.Z.
Oh, you guys are good. WP.S.Z, comma, and now what's our little e?
X and Y.
X and Y. Are you with me? So that's X and Y. And then what's our little f?
X.
X.
Don't forget the textual substitution
You forgot the equals.
after the semicolon.
Colon equals.
Oh, yes. Okay, now do I have to say, should we write this out?
No.
Nope.
Because if we write that out, it will be, the right-hand side of 383 follows from E equals F,
Which is X and Y.
which is X and Y equals X, yeah? So this follows from,
Well, will we leave it as equal vowels though? Or do we use equals?
well, this is the follows from.
Right.
And that has to be, it has to be equals, right?
Well, 'cause
3.83.
What we were using previously, we used equal vowels.
Oh, well, equals works for numbers and Booleans. In this particular example, we're using it as a Boolean, right? So X and Y equivales X. And now 360 equals 360 what? Oops. X implies Y. Boom! Now, is that cool or is that cool? Going all the way back to 360, Leibniz, boom, boom. You guys are good.
It's all right.
Okay? I think that's very nice. All right, now let's take a look at the next one.
You done 4?
Yeah, we're going to keep on trucking, man. All right. Oh, well, actually, I can't prove P.4 because what's another synonym for definition?
Oh, axiom.
Yeah, that's an axiom. So we can't prove P.4, but let's take a look at it. Here, let's take a look at it up here. It says definition Hoare triples. Well, what does it say? It says that Hoare triple Q, precondition Q, statement S, postcondition R. What does that equivalent?
Exactly what we've been saying. Is Q implies the weakest
Precondition S dot R.
If it's a valid.
If it's a valid one, yeah,
It's gonna work.
it's going to work. Is that nice?
Yeah, we've already. Yeah.
And we've already seen the meaning of it. I mean, we did some examples to get the meaning, but so there is the formal definition of a Hoare triple. So anytime you have a Hoare triple like this, you can just equivales. You can replace it with Q implies WP.S.R.
Nice.
Are we good? This is so.
4.1.
Oh yeah. Okay, so now let's look at 4.1. The 4.1 says, now what does 4.1 say? 4.1 says that anytime you have an S and an R, it says that WP.S.R really is a precondition.
It's P.
And it's true.
I mean, yeah, that does make it valid. I mean, in other words, it's kind of trivial, but we're proving that WP.S.R is a precondition. I mean, we know by definition, we call it the weakest precondition, but we're actually going to show that it
Do
is.
we have to use the whole thing? Because there's no equals or equivalents or anything.
You have to just get.
Well, I think we can do the whole thing, and yeah, I think we should use the whole thing. Because, you know, if we do, we can go back to the what? To the definition. Are you with me? So here, let's do theorem P.4.1. Like I said before, I added one to my original one, and I didn't want to go through and renumber all. So that's the meaning of the point extra. Anyway.
Let's start right out with P.4.
Okay, let me just make a comment about it.
No.
what this is saying is that WP.S.R is always a precondition. Okay, so WP.S.R is always a precondition. In other words, if you put it in front, WP.S.R, and then you have S for the statement and R for the postcondition, this Hoare triple is valid, right? This is going to be easy, I think. I mean, you guys did that one so well. I think you'll be able to fly through this one, right? So let's start with the whole thing. What do we have? WP.S.R, statement S, postcondition R. So obviously, what's the first thing we use?
P.4.
Yep.
WP.S.R implies, implies.
P.4. So this would be what? What does that make it?
WP.S.R.
WP.S.R.
Implies WP.S.R.
Oh, implies WP.S.R.
Oh,
Yeah, but now what?
Duh.
Well, you can't, okay, so are you saying equals duh? I don't think so.
Equals by.
Yeah, look it up.
Reflexivity of implied.
Ha-ha.
3.71.
Very good. So you got to get back into the groove of these 3.7 whatever. So did you say 3.71? 3.71 reflexivity of implies. So that's true, right? So boom, we're done. Or I guess we could have just said this, which is reflexivity of that style.
But then we have to do textual substitution.
Well, yeah. Okay. All right. Now let's take a look here. Let's take a look up here again at P.5. P.5 is called.
Is a rule an axiom?
No.
Okay.
A rule is a theorem. As a matter of fact, let's take a look. P.5, postcondition rule. It says Q, suppose you have the Hoare triple, Q, statement S, precondition Q, statement S, postcondition A, and you also know that A implies R. If that's the case, then what can you conclude? That QSR is a Hoare triple.
That's monotonicity. Or substitution or something.
It is something. As a matter of fact, you're going to show me what that something is because that's a homework exercise
That's the proof.
to prove P.5. Well, I mean, you have to do it
It's
formally.
like-
You have to do it formally.
It's like a 1 or 2 step.
Well, okay. All right. Now, the next one is the definition. So we're not going to prove P.6, but let's take a look at it. So the definition is P.6, definition of what it means for two programs to be equal. Now, let's go back and review a little bit. Do you remember what it meant for two sets to be equal? We had set equality.
All of their elements are the same. Or
It was,
the theorem was if X is in this one, then it's guaranteed to be in the other one.
yeah, it was a for all
For all
V, be an arbitrary V, what? V is an, what was it?
If V element,
V is an element of the first,
then it's an
equivaled, if and only if, V is an element of the second, right? Now look, you guys, check this out. Check out this, the way this P.6 is worded. Notice that we didn't say, in P.6, we did not use this. Here, let me make a comment.
It's
P-
written out in formal.
Yeah, it's written out. And now why can't we use this? My point is we cannot use this for all. Now why can't, do you see why we can't? So I had to write it out. We have to write it out or come up with a new symbol, but this is the only place we would use it, so. And why is it, can anybody see why we can't use the for all the way we did before?
Because R is an expression and not a variable.
Well, yes, that's exactly what it is. Because whenever you do this, it's the dummy variable. But here, R is not a variable. R is a what?
A Boolean expression.
Yes. So we cannot use for all because R because R is an expression. Okay? Not a dummy variable.
It's an intelligent variable.
Okay? So you can't have, that's why. And furthermore, you guys, what are S and T? Whenever we say equals, what's the type of S and what's the type of T?
Same.
Well, they have the same type, but what are they? Are they Booleans? Are they integers? What are they? What are S and T? Tell me what, can you? Yes. No, Alex was right. They are program statements.
Oh.
Are you with me? So remember, think about the types there. Okay, so S and T are program statements.
They look like sets to me.
Yeah, they do kind of look like sets from our previous notation. But anyway, what does it mean for two programs to be equal, to be equivalent? What does it mean for two programs to do the same thing? You're familiar with the fact that it's possible, like when your programming instructor gives you a homework assignment to write a program. How many, yes. Just about everybody in the whole class will write a different program. But it's possible that they all do exactly the same thing, but they're just written a different way. Well, what does this mean for two programs to be equivalent, mathematically equivalent? What does it mean for them to do the same thing always, for them to be the same? What does it mean? It means for all what? For all R, weakest precondition dot S dot R equivals weakest precondition dot T dot R.
Doesn't matter what the statement is as long as the postcondition is the same.
Well, as long as for all R, I can't say what it means other than just repeat what.
Okay.
You have to imagine every single possible. Okay, you have to imagine every single possible Boolean expression, right? Now, if that Boolean, if WP.S.R is false for this program, then it's false for that program. If WP.S.R is true for this program, it's true for that program. And you can take all the Boolean expressions in the world, and they have to be, if it's false for this, if the WP.S.R is false for that, it's got to be false for that. It's got true for that, it's true for the second one.
So in this case, those two programs equal each other, but they're not necessarily identical. They just do the same.
Exactly, and they don't have to necessarily be the same program, but they do the same thing if that's the definition of program equivalent. Now, does everybody now here? So here's the other thing. So now, do you remember Now let's remember this. You said it looked like sets. Now, do you remember how we proved two sets are equal? Remember we had to prove the what? The 9.8. Do you remember from remember proving the 9.8? How do you, the 9.8 lemma to prove two sets are equal? So what did we say? We said let what?
V be an arbitrary variable.
We said let V be an arbitrary variable and prove that what? V is a what?
Is an element of the first one.
V is an element of the first one, equivals V is an element of the second one. Well, that was based on the corresponding definition of set equivalence. So how would you prove that two programs are equivalent? You would say let what?
Big V.
No, well,
Or R.
let big R be a what?
Arbitrary.
Be an arbitrary
Precondition. Postcondition.
postcondition. Yeah, let big R be an arbitrary and prove that what?
For every R possible.
Well, no, and just do the lemma and prove that what? WP dot S dot R equivals WP dot S. So you would do you do the WP dot S dot R of the first one, and you would do the WP dot S dot R of the second one, and if you got the same thing for an arbitrary R, then you'd have it. So do you see how that is analogous to how we did sets? How we proved two sets are equivalent. All right. So look at P.8. P.6. What about P.7? Let's take a look at P.7. What do we have? Q implies A and
It's
the Hoare triple ASR. Oh, doesn't that look kind of like,
very similar to P.5.
right. Only this, the P dot 5 was, the postcondition A implies R. Here it's
The precondition.
Q implies A and the precondition
That's
ASR.
interesting. Q implies A, but then the precondition A implies precondition Q.
Yeah, but does that make sense? If
Yeah, I mean,
Q,
assuming A is the weaker of the two,
Right, A is weaker.
and it's still
yes,
it's
yeah,
still
yes,
valid.
yes, A would be the weaker of the two.
You'd probably use P dot 4 to prove that, right? No. No.
Q implies A and all implies.
Yeah, I'm not sure. I don't think I assigned P.7. But anyway, you can see how logically why it works, why that's the case, right? P dot 8 is a homework assignment. Ooh, this is kind of complicated.
I don't like the look of it.
Look at it. It's Q0, it's precondition Q0, statement S, postcondition R0, and precondition Q1, same S,
Same statement.
postcondition R1, but different preconditions and different postconditions, right? But it's the same S, right? That implies Q0, the conjunction of their preconditions
Oh, okay.
and the conjunction of their postconditions.
It's like P dot 2.
It's probably, yeah,
It's similar to P.2.
The postcondition part of it.
wasn't it similar to P.5 and P.7? Or maybe not. No, I guess not. Well, anyway.
Yeah.
Well, we'll find out because that's a homework problem. Okay, good deal.
All right.
This was good. See you next time.